Now we'll begin our next major section of technology, which is routing protocols at the icnd2 level. Back in icnd1, all we really discussed was RIP, because that's the basic routing protocol you can use to get a small network running. As we move into icnd2, we'll move into some of the more advanced protocols, such as OSPF and EIGRP. But before we begin, we need to understand some foundation concepts and hit a little review from icnd1 as we discuss distance vector versus link state routing protocols. This is a big class difference of routing protocols. Distance vector was what we saw in the icnd1, and now we're going to move into link state in icnd2. We'll first look at what distance vector routing protocols are all about and talk about some of their drawbacks. When we were in icnd1, we talked about RIP and we said this is what it does, but we really didn't see the dark side of the RIP protocol. That's what we'll look at as we see the loop prevention mechanisms. We'll then move into the link state routing protocols and what they're all about. We'll first start off with a little bit of review from the icnd1 world as we talk about the two umbrellas of routing protocols that exist, distance vector and link state. These two umbrellas really mark a big divide between the styles of routing protocols, and the best way I can compare them is to talk about my first car. My first car was a 1982 Volkswagen Rabbit diesel model. Now, nowadays, I look back and I think, man, I wish I had that car because gas prices are so high, and I think I got around 50 miles to the gallon. It was insane. But back when I was 16 years old and in high school, I didn't appreciate the car. I thought this car is not a babe magnet because that's admittedly, that's all you're really looking for at the high school age is just the cool car. And that car lasted me for years. As a matter of fact, I sold it when it had 200,000 miles on it, and it was still running. I never changed the oil. I just put gas in. I never did any maintenance at all. It just kind of went. The drawback to the Volkswagen Rabbit, but besides the babe magnet factor, was the speed. I timed it once. To a high school male person as myself, the 0 to 60 time of your car is very important to see how fast you can move. And I timed it, and that car got 0 to 60 in 42 seconds. I still remember it to this day. I thought, how horrible. But that's what distance vector routing protocols are all about. They're extremely easy to configure, meaning, just like my car, it didn't really take much to get in there, although I had to learn to drive stick shift and what glow plugs were all about. You just kind of turn them on and they work, and you don't need to maintain them. They just keep running. The problem with them is they're not very fast and they don't have many features. The two examples of distance vector routing protocols are RIP and IGRP. The RIP protocol we set up in icnd1, IGRP is gone. Cisco has officially discontinued support for IGRP. It's not even in the newer iOS versions. That's because nobody really used it. They moved on to link state. Now that is the Dodge Viper, the screaming fast car that takes just a ton of cost to get running, meaning a lot more knowledge to run that car than just a Volkswagen Rabbit, and there's a lot of maintenance and tuning and tweaking that has to go into it. And in the same sense, with link state routing protocols, they're very difficult to configure. As a matter of fact, we're going to get into the OSPF protocol and talk about configuring it, and we'll even set it up, but to really fully understand OSPF, that's what the CCNP courses are all about. The BSCI focuses tons of information on OSPF that expands on what we're going to lay as the foundation here. So they are feature-rific. They have a lot of stuff that they're able to do and a lot of speed criteria that they can handle. And the two examples are OSPF and ISIS. ISIS was the routing protocol for the OSI protocol. A lot of people just think OSI was a model, but there is an OSI protocol that is out there, and it's even better than TCP/IP, but not many people use it. Now, down at the bottom, you see the hybrid. And this is the Dodge Viper Rabbit, if you will. It's the best of both worlds. Really easy to configure, but gives you all the features of a link state protocol. The Achilles heel of this hybrid routing protocol is that it is proprietary, and the one example of it is EIGRP. Cisco made it, and only Cisco runs it. So you have to have Cisco routers everywhere to support that protocol. Let's first focus on distance vector routing protocols in their simplicity and in such a way that we can see some of the weaknesses that were not exposed in icnd2. Distance vector routing protocols by nature send their entire routing table at specific intervals. The one protocol that's left, which is RIP, sends its entire routing table once every 30 seconds. So you can think of it as imagine yourself standing in front of a big room of people, and you step up to the microphone every 30 seconds and say, "Hello, everybody in this room. I know about 192.168.10.20.30.40." And then you go and take a seat and wait 26 more seconds and walk back up to the microphone and spin that 30-second interval and you say, "Hello, everybody. I know about 192.168.1.2.3.4," and so on. And then you sit back down. That's exactly what RIP is doing. It's broadcasting or multicasting, depending on the version you're using, to the entire network once every 30 seconds to let them know what it knows about. So if we're running RIP down here, I have a interval once every 30 seconds. I'm saying, "Hello, everyone," out both interfaces. I know about 192.168.1, 2, 3, and 4. Now this router over here gets it and says, "Oh, great. Well, I knew about 2, but I didn't know about 1, so I'll add that to my routing table." It's a little review from icnd2 how routing tables are built. And so before long, all these routers know about their routing table. Now keep in mind, the reason that RIP sends updates every 30 seconds is not just because these routers might have missed something. That's because its update system is the only keep alive it has. Meaning if this router stops hearing updates, it's going to realize, oh, well, this router over here, we'll call him router C, is dead. So I will see if I have backup routes to reach the 192.168.1 network that router C was being used to support. So those updates are keep alives, and in their simplicity, RIP or distance vector protocols have looping issues. Here's what that means. Let's imagine that router C over here has, sent out its update. It's doing the normal RIP thing, and over here is the building that it's supporting. We'll say it's in Arizona. And that's the network. And the IT admin in Arizona comes in. It's 7 in the morning. He just happened to beat rush hour, so he came in a little early. And that administrator is walking up into the IT room, has got his cup of coffee, sipping the coffee and just, trying to wake up. Network admins are not morning people. They are creatures of the night because that's when most of your maintenance windows are happening. And he walks up, trot, 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 sees this dangling cable, but sees it too late. Trips over this Ethernet cable connecting the router to the switch and the rest of the network over here, and severs the cable. Snap, and sparks are flying and fire extinguishers. It's not that bad, but either way, router C loses its connection to the 192.168.1 network. Now, unfortunately, router C just sent an update 2 seconds ago. So it's got 28 more seconds to go before it sends out its next update and lets everybody know that the network is down. Well, here's where the problem comes in. Router B just happened to send out its last update 25 seconds ago. So it's got 5 seconds left until its next update. 4, 3, 2, 1. Hello, everybody. This is router B now. I know about 192.168.4, 3, 2, and 1. Truck, 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 truck. That update hits router C. Router C gets it and goes, well, that's fantastic. Router B, you must have been reading my mind because I just lost my own connection to 192.168.1. It just went down. So what I'll do is I'll point to you as the next hop address. We'll say router B is 192.168.2.2 over here. So router C will point to router B as the next hop address to now reach 192.168.1.0. Now you and I are looking at this diagram going, why are you doing that, router C? What are you thinking? Don't do that. Router B was using you to get to the 192.168.1 network. Why would you try and use router B? But unfortunately, distance vector routing protocols aren't that smart. So router C points to router B to reach the 192.168.1 network, and 28 seconds later sends out its own update saying, hey, I now have a new path to get to 192.168.1. It is through router B. That's the way that I go, and it's 2 hops away from me. Now, let's check this out. Before, router C was directly connected, so it was 0 hops, right? That's RIP's metric. It's hop count. So it was directly connected, 0 hops. So for router B, it was 1 hop, meaning router B would go hop, router C, and I'm there. That was the process router B would use. But now, router B sent an update to router C saying, I have a link to 192.168.1, and it's 1 hop away from me. Router C got that update and says, well, if it's 1 away from you and I go through you to get there, it must be 2 hops away from me. Does that make sense? Because router C thinks I hop through router B and then go wherever router B goes, and then I'm there. So router B gets the update, right? It says, okay, I now am hearing about 192.168.1.0 from C, and C is now claiming that it's 2 hops away. Router B is scratching its head and goes, well, that's funny. It used to be 0 hops away from router C, but now it's 2. So, well, I guess if it's 2 hops away from router B, it must be 3 hops away from me because I used router, oops, I meant router C. If it's 2 hops from router C, it must be 3 from me because I used router C to get there. That's odd. And it passes that update to router A over here, and router A gets it and says, well, that's funny. It used to be 2 hops from me, but I guess now that it's 3 hops from you, it must be 4 hops from me. And this system goes round and round and round and round and round. And these hop counts keep going up higher and higher and higher. This is known, its symptom is technically called a countdown to infinity. Now, you and I know you'll never reach infinity, and that's why we call this an official routing loop. This is something that distance vector routing protocols such as RIP can experience. Thankfully, built into Cisco routers are 5 loop prevention mechanisms to keep what I just showed you from happening. Now, this will prevent every routing loop that you can have. So that leads to the question, or begs the question, why do we need to know about these? Well, the reason why is they do help stop routing loops, but they can also cause problems, and there may be times where you have to turn 1 or 2 of them off. So the first loop prevention mechanism that we have is a maximum distance. With RIP, the maximum distance that's defined is 16, let me grab my pen here, 16 hops. So once a RIP network is 16 hops away, it is then considered dead. So if we had a loop that did happen in router, let me put my letters back here, C, B, and A, we're passing that 192.168.1 network all around the network. That would keep going until they reach 16 hops, and then whichever router got it at the 16 hop level would say, oh, that route is now dead. It's too far away. That also tells you that RIP can only be used on small networks because there are some networks that have links that are farther than 16 hops from each other. The second one that you see is route poisoning. Route poisoning kind of integrates with the maximum distance. And what it does is advertise that the network is down immediately. So it seems kind of funny, but routing protocols built in themselves do not have a way of saying this route is down. That's not what they're designed to do. Routing protocols are designed to tell each other what routes are up. So route poisoning had to be specially engineered to say, router C, as soon as this network goes down, poison it, kill it. And the way it kills it is by setting it to a maximum hop count. You know, it kind of triggers another rule. These rules integrate tightly together. So as soon as that network admin trips over the wire over here in Arizona, it poisons the route and says, well, this is now 16 hops away, and the next update that goes out will advertise that. So router B gets it and says, oh, well, that's the maximum, so that route must be dead. Now, the third one is just logical. One of the reasons this whole system happened was router C sent an update 2 seconds ago, right? And so when this network went down, it had to wait 28 more seconds before the next update went out. And with that delay, router B was able to send an update and say, hey, router C, I've got a route to 1.0, and that caused the whole problem. So triggered updates integrates with route poisoning, which integrates with max distances, which says when that network admin trips over the wire, immediately negate all timers. All bets are off at that point. You've had a major network change. So at this point, we will trigger an update. Overrule that 28 seconds you were going to wait, router C. And as soon as you see the network go down, send a poisoned route telling router B the network is down. Split horizon. Split horizon is one of the most difficult to remember, but one of the most critical ones, and one of the ones that causes the most problems when you are using these loop prevention mechanisms. If there's one that you're going to disable, it's probably split horizon. And when we get to some of the advanced WAN networks, I'll bring this back up. What split horizon does is tell routers, do not send updates back in the same direction you received them on networks that are being advertised. Now, let me explain that in plain English. Let's say that you and I met on the street, and you came up to me and said, "Hi, Jeremy. My name is Mike." And I said, "Hi, Mike." And you said, "Jeremy, I have brown eyes." Now, would I ever tell Mike that he has brown eyes? No, because that would create a people loop. Meaning, if Mike and I were to meet on the street and Mike said, I have brown eyes and told me about that, I would never tell Mike he has brown eyes for many reasons, but primarily because I don't want to start a people loop because I would say, well, yeah, you have brown eyes. And Mike would say, yeah, I do. And I would say, no, you have brown eyes. And we'd just keep going around and around until both of us, Mike and I, died. So split horizon is a rule that says do not tell routers about routes they told you about. So when router C says, hey, router B, I know about 192.168.10/24, router B is now banned from telling router C about that route. Brilliant. Because that's how this whole thing started in the first place, right? Router C heard about a route that it told router B about. And that's what caused router C to point to router B and started the whole loop from beginning. Now you'll see when we get into some of the advanced WAN network diagrams why this can cause some problems, especially in networks like frame relay. But for now, split horizon is definitely a good thing. Last but not least is the hold down timer. Your best and worst friend when it comes to loop prevention. Hold down timers says, I will not believe any other updates about this route for X amount of time. Here's what I mean. When this network goes down, router C sends a triggered update saying it's down. Router B receives that and says, well, that's a big change. Let me immediately tell router A about it. And both of them will set a hold down timer. This is my little clock. Now that hold down timer can vary depending on what protocol you're using, but what it does is it says, I will not accept any more updates about this for a certain amount of time. The reason that this is in place is because of flapping interfaces. If you've never heard of a flapping interface before, what it is it's an interface that goes up and down and up and down and up and down and up and down 1,000,000 times a second. Well, maybe not that many, but a lot. Just constantly going up and down. It's caused by a bad network cable. It could be a bad connector. You know, it's not plugged in quite all the way, but it's in most of the way. Or it could just be a network interface card, a network card that's going bad. Now, the problem is we introduce this system of triggered updates. Well, if we've got that, that can destroy a network when combined with flapping updates or a flapping interface, because when this goes up, immediately router C is like, hey, router B, it's up. Router B is like, hey, router A, it's up. Oh, nope, it's down, down, down. And everybody's adding and removing that route 1,000 times a second from their routing table. All the routers on your network has their processor utilization shoot through the roof. So what hold down timers do is say, okay, you told me it's down. I will not believe anything else about that. Now, that's great in the sense that you've prevented flapping interfaces, but it's bad in the sense that you've got this IT admin, right, who tripped over that cable, and he sees it. He goes, oh, I can't believe I did that, and plugs the cable back in. Well, immediately router C is going to say, oh, okay, it's back up. But router B is not going to believe that. It's going to say, sorry, you've told me it's down, and I'm going to believe it's down for X more seconds. I think by default on a Cisco router, it's 180 seconds. 180 seconds. Can you believe that? That's a huge amount of downtime just because someone unplugged a cable and then tried to plug it back in. So all of those 5 things are loop prevention mechanisms, and they are all drawbacks of using the RIP routing protocol. Now let's change our focus to the link state routing protocols, which have no loops because they have a completely different system of handling routes and route updates. First off, link state routing protocols form neighbor relationships with each other rather than just sending broadcast or multicast packets to everyone. So, for example, I gave you the example of a distance vector routing protocol being like you walking in front of a group of people into a microphone and saying, hey, everyone, I know about these networks. Well, in a link state routing protocol, if it was the same situation, you would stand up on the stage and then you go, you know what? Let's not do this. Let's walk down, and you would find the first person in that crowd that you would want to exchange routes with, and you would say, hi, my name is Jeremy. What's yours? And they would say, hi, my name is Michael. And you would say, well, Michael, it's funny. I'm doing this odd system where I'm saying you, but it's really me. So how about I flip it to me? I would say, hi, Michael, I know about these routes. And Michael would say, great, let me put them in my routing table. Jeremy, I know about these routes. And I'd say, great, let me add those to my routing table. And then we just look at each other, and I would say, hi, Michael. And he'd look back and say, hi. And then I'd wait. And then I'd say, hi, Michael. And he would say, hi. And we keep doing that all day long. Hi, hi, hi. That's actually the technical name of a protocol called the Hello protocol. OSPF uses this protocol known as Hello, and it sends it much more frequently than RIP to make sure that the router is still online. Since I'm just sending a single message to another router, I'm just saying hello, I can send that much more often than RIP could when it was sending broadcasts and multicast packets because it bothered the whole network. If you were to tune RIP down to send those more often, you would cause some major network problems. So, OSPF and other link state routing protocols use hello. After the initial routing tables are exchanged, routers just send small event-based updates. Meaning, with distance vector, we sent the whole routing table every 30 seconds. With link state routing protocols, I only send an update when I need to send an update. When something changes, I would say, hi, Michael, 192.168.1 just went down. And you go, oh, that's great. I'll remove that from my table. And then I just look at him and go, hi, Michael. Nothing more. I don't need to send any more updates, unlike RIP. So there are only 2 link state routing protocols that exist today. That is OSPF, that's what we're going to talk about here, and ISIS, which is covered more in the CCNP curriculum. So to wrap up this conceptual video on routing protocols, let's look at the advantages and disadvantages of using a link state protocol. Advantage, they are much faster to converge. They can find problems in the network and repair them much faster than distance vector. And the reason why is they're saying hello more often so they can detect a failure much quicker. There's no routing loops because the routers have a complete roadmap of the network, which we'll see as we dig deeper into OSPF. So they don't ever get confused. They don't ever need loop prevention mechanisms. If you've got a roadmap, there's no chance that you're going the wrong direction unless you don't know how to read a map. Finally, it forces you to design your network correctly. And I have that as both an advantage and you can see a disadvantage. That's because link state routing protocols do require a solid network design. Meaning, if you've designed your network poorly and just assigned IP addresses where you wanted to assign them, put a network here, put a network there, no real design in mind, well, link state routing protocols are really not going to be an advantage to you at that point because they will cause worse problems on your network than if you had used distance vector. So some of the disadvantages is number one, they do consume more resources on your router. They'll use more processor and more memory utilization because they're simply more complex. They do require a solid network design, and I'm skating around that one for now, the deep definition of that, because as we look at OSPF specifically, I'll show you what a good design looks like. Finally, link state routing protocols have technical complexity. There's a lot to them, and there's a lot to know about them if you want to use them efficiently in your network. So there is a lot more education necessary to use link state protocols. We've now taken our first step back into the routing protocol world since the icnd1 videos, as we've looked at distance vector versus link state. So let me summarize. We looked at the two classes or umbrellas of routing protocols. All in all, distance vector you can think of as easy to configure and featureless, meaning they don't have that many features, whereas link state you can think of as complex and require a lot of tuning, but they do have just about every feature you would expect from a routing protocol. So that's the difference. We then looked at the loop prevention mechanisms of distance vector, which are really a band-aid for some of the problems introduced with the routing protocol that broadcasts in all directions everything it knows every 30 seconds. Finally, we looked at the advantages and disadvantages and what the big difference is when using a link state routing protocol. I hope this has been informative for you, and I'd like to thank you for viewing.